Got it.
Okay, welcome everyone, and introducing Frank. He's the Section Emergency Coordinator in Eastern Washington. And so he's going to be doing our presentation today. And Ray, did you enable screen sharing for him?
Yes, I did.
Okay.
Oh, let me see here first before I go there. Go here. This. Oh, come on. That's not what I wanted. There you go. Go here, no there. Go there. Share. Oh, come on. Okay, there's that. That's not the screen I expected. Okay, I take it you can see my screen. I really thought I had a different, just a moment here.
So we're seeing it, but you need to go into presentation mode.
Yeah, I know. I'm in presentation mode. There. Are you
There it goes. We got it now.
What?
We got it now.
Okay, goody. Okay, before I actually go into the questions and what the responses are and everything else, there's a few things I'd like to go over first. These are fundamental things about radio waves. And the reason for that is because if you understand these basics, a lot of the questions are self-explanatory. Okay, electromagnetic radiation or radio waves, because the radio waves are part of the electromagnetic spectrum, basically means that you have both an electric field and a magnetic field. And this image right here shows you the classic example that's used. The electric field and the magnetic field will be at right angles to each other. Yeah, they are sometimes, but that's the example we use, and this is what everyone will be using for explaining, or the exams will be based on. You have the wave going in one direction, as you see with the black line there. Magnetic field and electric field are at right angles to that. And they may be just in one orientation, or they may be rotating. They do a lot of different things. I'm not going to go into those details because it's not important for what you're learning. But just know that you have an electric field and a magnetic field, and everything in amateur radio, with maybe one or two exceptions, is based on this picture. So this is another way of looking at it. You have a wave. It's just whipping along in time. And I'm going to use this to explain a few concepts which will help you. First of all, this is standard, the sine wave is usually what they use. And you might have like two signals or two sine waves that are coming along. And if they're in phase, and if you look at this, you'll see that this peak and this peak and this peak and this peak, the peaks are all in phase, and so is everything else. And if you do, you combine those two and you get a big wave. This is when they are converging and they are basically joining together. Or they can be out of phase. If you look at this screen, what did it just do? Oh, okay. This wave is out of phase with this one, which means it's exactly out of phase. That's what we call 180 degrees out of phase. So if you combine these two together, you have a peak here and a bottom here. Well, that adds up to 0. And so you get a null signal. Now, the other thing you have is, okay, you have a wave coming along and it might run into something and it'll be reflected. I should have turned this one here around vertically. Didn't think about that. So it comes in and reflects off that and goes. Now, I deliberately use sort of a dotted line here because if the holes are big enough, the wave won't reflect. It will just pass through. So the size of the holes are important. In this case, the holes are small enough where the wave just gets reflected. Well, another thing that can happen is that the barrier can be kind of weak and the wave comes along and it hits that barrier. Yes, you get a reflection, but some of the wave also goes through and gets refracted. That means it gets bent and moves off in a different direction. Okay, so those are some very basic concepts, and I'll use those over and over again as we go through these three sections. Any questions on this? Because I can't see anybody at the moment. If I'm going too fast, let me know. Nobody cares. Okay. Yep, I heard that. Okay, there are three sub-elements here, and there will be 3 questions on the exam that you have to answer on these things, one from each one of these sections, A, B, and C. The first one is all about radio wave characteristics, how radio signal travels, fading, multipath. Gosh, all this stuff, what are you talking about? This goes back to what we did in the very beginning. Why do VHF signals sometimes vary greatly when antennas moved only a few feet? I had something net a couple of days ago where someone moved like 3 feet and they were heard perfectly, whereas before they weren't. That's because what you have is you have the signal coming out and it has multiple paths. You might have a straight line path and think, well, that'll be a good signal, and it would be, but there's all of these other ones coming over here, bouncing off of buildings or whatever, and they arrive at the receiver. And remember how we talked about how the 2 waves, when they come together, they can either reinforce or they can cancel. That's what happens here. And it's called multipath propagation. What's the effect of vegetation on UHF and VHF, or UHF and microwave signals? Think of your microwave. What do you use your microwave oven for? Anybody? Nobody has a microwave oven. Okay. You have absorption at those waves, at those frequencies rather, at UHF and above. You will have absorption by organic materials. And so that means that the signals are absorbed by the vegetation, which means that, hey, in the wintertime, when there are no leaves on the trees, they will go farther because they aren't being absorbed. Okay, what antenna polarization is normally used for long distance CW and single sideband contacts on the VHF and UHF bands? This again, this is the direction that the electric field is in. Usually for VHF and UHF, everything is horizontally polarized. That's the direction that the electric field is vibrating in. That'll be horizontal. It can also be vertical, but everyone uses basically a horizontal polarization for these type of contacts. Now, here comes the next one. What happens when antennas at opposite ends of a VHF or UHF line of sight radio link are not using the same polarization? What would you guess? If one's going vertical and the other's going horizontal, do you think the differences would be just as good? No. The received signal strength is reduced, and it can be as much as 20 dB. Now, when you look at that 20 dB, you might say, well, gee, what does that mean? Every 10 dB is a factor of 10. So 20 dB is 10 times 10, or a factor of 100. Okay. When using a directional antenna, how might your station be able to communicate with the distance repeater if buildings or obstructions are blocking the direct line of sight? And anyone want to guess? Yeah, I know the answer is right there. You use reflections. If you don't have a direct line of sight, you try to bounce your signal off of something that will reflect the radio waves. Now, what is the meaning of picket fencing? I'm going to be honest with you. There are terms that you just have to learn what they mean. We're speaking a different language. Well, if you have, as a kid, did you ever take a stick, walk along your picket fence, and just run the stick along the picket fence? It goes click, 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 click. That's what's happening here. You have the radio waves are hitting the pickets and being reflected, and they're sort of hitting the spaces and going through. So what type of signal are you going to get as you go through that motion? There'll be a rapid flutter, strong, weak, strong, weak, strong, weak. That's rapid flutter. It only happens on mobile signals. Either you're moving or the target is moving. Okay.
So Frank,
Yes.
I consider that answer to be a big city answer. Because when you're out in the boonies and you have exactly one repeater and no things for the signals to bounce off of around you, it is actually just in and out of the coverage area.
Well, it can be. Let me say, it happens most often in the city or suburban environments, but it can happen out in the boonies if you have the right environmental conditions. And it might be anything from the mountains that surround you or whatever to structures that might be out there. For example, you'd be passing by a bridge or whatnot. Or other vehicles, that could be another problem. But again, what I want you to understand here is that picket fencing, think of a picket fence. You have a picket, you have space. You have a picket, you have space. You have a picket, you have space. Picket fencing means that you have something which is going to be reflective, not reflective, reflective, not reflective. And that is what's happening here. What weather condition might decrease range and microwave frequencies? Now, most people don't realize it, but microwave ovens are designed to basically heat up water molecules. And so precipitation is water molecules in various forms. And so that will, since it absorbs the microwave frequencies, it will decrease the range. What is the likely cause of irregular fading of signals propagated by the ionosphere? Again, this goes back. We're combining different signals. Because remember, when you broadcast with your radio, you're going out in all directions. So if the signals go out and they bounce off of other things and they have the straight line, they all come together at the receiving point, or you're receiving it from something which is broadcasting because it goes both ways. Those signals coming from different paths will combine. And how they combine depends on where you are relative to the transceiver. So you might have the signal be real strong and then weak, strong and then weak. Okay, which in the ionosphere basically is just part of the atmosphere, and due to changes in the density, due to temperature or ionization, the radio waves can bounce off of it. Which of the following results from the fact that signals propagated by the ionosphere are elliptically polarized? Okay, elliptically polarized. First means that, remember how we had the picture of the electric and magnetic fields at the very beginning? They're right angles to each other. Well, elliptically polarized means this is one of the times when that picture doesn't hold true. They're sort of rotating, or they're not perpendicular to each other. And that's, in that case, because they're changing and they're not just strictly vertical or horizontal, that means that either vertically or horizontally polarized antennas may be used for transmission or reception. Now you might ask yourself, well, if that's the case, why don't we always use elliptically polarized antennas? Well, the thing is, one, they're difficult to make, and two, they are not as efficient as a vertically or horizontally polarized antenna, depending on the situation. Okay, what effect does multipath propagation have on data transmissions? Again, going back to our examples at the beginning, if you have multipaths, what's happening to your signal? It's going to be strong or weak. So it'll be varying. Now, if you have someone who's talking to you, and sometimes they're yelling, they're talking real soft, and sometimes going back and forth, like, how well are they able to transmit information? In this case, your error rates are going to increase. I hope I didn't wake anyone up with my example there. Okay, what region of the atmosphere, or which region of the atmosphere can refract or bend HF and VHF radio waves? And the answer is the ionosphere. Give you a hint here. The name ionosphere, ions are charged particles. So that's why you have the reflection. Now, why is it just HF and VHF radio waves? Because UHF and above will go right through it. Remember that idea of the picket fence? The radio waves are short enough that they can fit between the pickets and not bounce off the pickets. What is the effect of rain and snow, or fog and rain, on signals in the 10 meter and 6 meter bands? Yeah, not much. Again, because they don't interact with the water molecules like UHF and microwave frequencies do. No questions on any of that. You're going to get one question out of all of those, I'll say. So you have 12 questions here. One of them will be on your test. Is there any questions about those? Everyone's fallen asleep or they've left the station. Okay. Electromagnetic wave properties, wavelength versus frequency, nature and velocity of electromagnetic waves, relationship of wavelength and frequency, which is kind of a redundant thing there. Electromagnetic spectrum definitions, UHF, VHF, and HF. Okay. The first one, what is the relationship between electric and magnetic fields of electromagnetic waves? They are right angles, just like that little picture that we showed. And what property of a radio wave defines its polarization? We talked about this. It's the orientation of the electric field. The electric field is used as the reference. Oh, that looks like a familiar picture. What are the components of a radio wave? It's electromagnetic radiation. So the name tells you everything you need to know. Electric, magnetic. What is the velocity of a radio wave traveling through free space? Well, radio waves or electromagnetic radiation, and everyone just calls that the speed of light, because light is electromagnetic radiation too, just at a very, very short wavelength. And the speed of light is actually like 299 blah, 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 blah meters per second. We just round off and say 300 million meters per second. should remember that number, 300 million meters per second. And we do that, I do that deliberately so that you'll see why later when we start talking about our frequencies are in megahertz. So if you're 300 mega meters per second and you're in megahertz, then it becomes easy to calculate the wavelength. What is the relationship between wavelength and frequency?
You need to look like a little black dot.
I'm sorry, I didn't hear that.
The freeze light, and when you move the light away, the move.
I think someone's got their mic open. They're not talking to us. All right.
Wavelength and shorter frequency.
Yeah. And you'll see there's a formula later which very clearly illustrates this. In fact, you got the pyramid down below. If you take a look at wavelength, if you look at wavelength, it's the frequency times the wave speed is equal to frequency times wavelength. That means since the speed of radio waves doesn't change, with some caveats, that means that if the frequency goes up, the wavelength has to go down, and vice versa. If the wavelength goes up, the frequency goes down. And so you have that formula. Converting frequency to approximate wavelength is the wavelength in meters is 300 divided by the frequency, or you say 300 times the wavelength in meters times the frequency in megahertz. And I'll have to tell you that I was one of those nerds. I loved algebra in junior high and high school, and I don't even bother with these pyramids. I love the equations. They speak to me. In addition to frequency, which of the following is used to identify amateur radio bands? The approximate wavelength in meters. Now we say the approximate because they're not precise. For example, we talked about the 80 meter band. Well, the 80 meter band isn't exactly 80 meters. It's a little bit less than 80 meters. So, but we say 80 meters because it's a lot better than saying, let's see, 300 divided by 3.95. That would be yeah, no, we don't do that. We just round up or round to the nearest whole number. Now, the next one is illustrated by this nice little chart here. You have to remember your powers to 10 and the number 3. You start is what frequency range is referred to as VHF. Well, that's 30 megahertz to 300 megahertz. And if you look at it, you have ultra high frequency, which is 300 to 3000 megahertz. VHF is 30 to 300. Difference of 10 there in decades. HF or high frequency is 3 to 30 megahertz. Medium frequency is 0.3 megahertz to 3 megahertz. And below that is low frequency. Guess what that is? Anybody? If we're going down by decades, what's the upper reaches of the low frequency to be 0.3 megahertz? What would be the lower limit of it?
Would it be -3?
No, you can't have a negative frequency.
So it'd just be 0 then?
No, it'd be 0.03.
Oh, okay.
That'd be 30 kilohertz. Now, you have very low frequency, which is getting down from 30 kilohertz to 3 kilohertz. Scientists are weird, so is engineers. Now, let's go to super high frequency. That's right above ultra high frequency. What would that be? Look at the UHF. What would be the next band up?
Move your decimal point.
Yeah, move it over just a factor of 10. Be 3,000 megahertz to 30,000 megahertz. Now you're getting up into the gigahertz. So, for example, 3,000 megahertz is 3 gigahertz, just so you know. Okay, what frequency range is referred to as UHF? Well, we see it right here, 300 to 3,000 megahertz. If you're wondering why they do it in powers of 10, it's because it gets harder to, you have a certain bandwidth that you have for your signals. For example, in HF, you're looking at a bandwidth generally of about 2 to 3,000 hertz, 2 to 3 kilohertz. In VHF, you're looking at generally like 6. Now let's see, that's the separation. Now you're looking at about 5 kilohertz for that. You get up to UHF and it gets higher still. The reason why we like getting up there is because we can have pass more data faster. All right. What frequency is referred to as HF? Again, 3 to 3. You go back here to this little chart right there, right in the middle. And if you know that, you've got everything. And basically, you got to realize that back in the day, when they first started doing radio, medium frequency was, wow, that was pretty high. And so they said, if you go above that, well, that's high frequency, and we're never going to get beyond that. Then World War II came along and they started getting to VHF, and then they got to UHF. So, okay. What is the approximate velocity of a radio wave in free space? 300 million meters per second. So there you have 11 questions. You'll have one of those. And this is probably the easiest section on radio propagation you're going to have, because it all goes back. No, I don't have the equation. Well, this one right here. You have the wave speed, which is 300 megahertz or mega meters per second, is equal to the frequency in megahertz times the wavelength in meters. Any questions on that? Okay, let's talk about propagation modes. Sporadic E, meter scatter, aurora propagation, tropospheric ducting, F region skip, line of sight, and radio horizon. All of these, I'll go back to the introductory portion where you take a look at radio waves and what can they do? They normally, radio waves travel in straight lines, except in the case where they can bounce off something or they can be refracted. And this section is all about either reflecting or refracting. Okay, why are simplex UHF signals rarely heard beyond their radio horizon? Because they don't bounce off the ionosphere. They go right through it, usually.
What if we're snowing?
What's that?
What about if we're snowing a lot?
I'm sorry, can you speak a little bit louder?
What about if we're snowing a lot?
Well, okay, we're talking here about UHF. UHF is attenuated by water. So if it's snowing, what's going to happen to your UHF signal?
Bouncing off?
No. What's snow composed of? Water.
It's probably snowing where Michael is right now, so he can look outside.
Yeah, just go out there with 2 radios and see if they can talk to each other. No, I'm teasing.
Yeah,
No.
so sad.
The UHF signals in snow will be attenuated, like they will in rain or clouds. So that's all water. And UHF, basically, when it runs into water, what it does is cause the water molecules to start spinning. That's done on the molecular level. And spinning water molecules is a form of hot water. That's basically what you do in your microwave oven. You're heating up the water molecules by imparting energy to them, and they start spinning and vibrating. And so that's how they get heated. So, but no, UHF, you got to realize that goes in a straight line and it doesn't bounce off the ionosphere. Okay, what is the characteristic of HF communication compared with communications on VHF and higher frequencies? Again, HF has a long wavelength. This goes from like 80 meters down to 10 meters. It's going to hit the ionosphere and it's going to bounce. And I think we have a picture of that here later. What is the characteristic of VHF signals received via aurora backscatter? Okay. What they're referring to here, aurora backscatter, is when you have like the aurora borealis, the northern lights. Those are just charged particles in the upper atmosphere. And they get excited. They get a lot of them excited. And that acts like a mirror to VHF signals. So what happens is that you send your signal out, it hits that aurora borealis, and it gets reflected. And what happens when you get multipath propagation, which is what this is? You get your signals are going to get screwed up. So the answer is they are distorted and signal strength varies considerably. Which of the following types of propagation is most commonly associated with occasional strong signals on the 10 meter, the 6 meter, and 2 meter bands from beyond the radio horizon? This goes back to the ionosphere, and you have a layer of it called the E layer. And occasionally what happens is that they'll get really excited. The ions in there are going to get a very high density. And when you have a high density of ions, the radio waves on the 10, 6, and 2 meter bands are going to be reflected much better than they normally are. That is called sporadic E. Why is it sporadic E? Because it happens sporadically. That's sort of a circular argument, but that's what's happening here. Okay, which of the following effects may allow radio signals to travel beyond obstructions between the transmitting and receiving stations? Okay, remember how we started at the very beginning? We said radio waves can either bounce off objects or they can be refracted. Well, this is a case of where you can have a type of diffraction, which is called knife edge diffraction. Whenever you have a sharp edge, like the top of a mountain, the radio waves come up there, hit the top of the mountain, that edge, and they get re-radiated from that point. Just as this diagram shows. See, the radio waves comes up here and then it gets re-radiated. And so the person over here might be able to hear this station over here, even though they have a big old mountain between them. It's not always reliable, but it can happen. What type of propagation is responsible for allowing over the horizon VHF and UHF communications to ranges of approximately 300 miles on a regular basis? Okay, this is a situation where you have the upper atmosphere acting kind of weird. You have to understand the atmosphere is not a homogeneous thing that gets, the air gets less rare or rarer as you get higher up. Sometimes you have inversions, temperature inversions. As you go up higher, the temperature gets hotter rather than colder. Well, when that happens, the density of the air changes. And what happens is that the radio waves can go into that layer that's formed, and instead of passing through, they start bouncing off the sides of that those layers. As this picture shows, here you have it like an inversion layer right here, and the radio waves come in and they bounce off the upper one. Okay, we kind of expect that. And then they bounce down. Oh, wait a minute, they're bouncing off the lower one too. So they just keep bouncing across until they find a way out. And that's called tropospheric ducting, because where it happens is in the troposphere. And unless you want to have a nice discussion of meteorology, we won't go into that. But the troposphere is up there, kind of think of it like the ionosphere. It's up there somewhere and you're just bouncing off of it. Okay, now we come up with something else. Which band is best suited for communicating via meteor scatter? You might say, okay, what do you mean meteor scatter? We have meteors entering the Earth's atmosphere every day, all day long. Most of them are small grains of sand flying in at fantastic speed. Occasionally you'll have bigger ones, and you have the biggest ones of all that killed the dinosaurs. Well, when they start entering the atmosphere, they start burning up. And as they burn up, the atoms that make up that meteor become real hot, and they start throwing off their electrons. They become ions, and they leave a trail of ions in the atmosphere. It turns out that 6 meters is ideal for bouncing off that trail of ions. So that is the band that's best for meteor scatter.
What if we're in a real quarter environment?
I'm sorry, what's that?
What about if we're in the real quarter environment, like you said, that would help with the lower borealis, right?
I'm sorry. I'm not quite
For the
understanding.
transmission.
You're kind of muffled. Go ahead.
Yeah, 'cause, what about if we're in a quarter environment?
What do you mean a quarter environment?
Like we get cold temperatures, would that affect the waves?
So Frank, he's in the along the Bering Strait in Alaska, and that's why he's having trouble with the phone connection. But they're far enough north to get a regular aurora borealis, and I think that's a little bit more what he was asking about there. And I think, his location would really be fun to try that.
Well, yes. Yeah, you're far enough north where you're probably going to see aurora borealis a lot more than we do. Meteors happen all around the world. So you have meteor scatter occurring all around the world. Although I will say that if you, I think if you look in the eastern sky early in the morning, you're more likely to see meteor scatter than in the late afternoon, early evening. And that's because the Earth then is going sort of into space, and the meteors kind of are in the way. So the Earth hits them, you think that way. In the afternoon and the early evening, the meteors have to catch up with the Earth. But in all this, whether it's meteor scatter or aurora borealis, what you're looking at is a layer of ions that are being formed that you're able to bounce your signals off of. And whatever causes those ions, that layer of ions, is going to be good for extending the range of your transmissions or reception. Does that answer your question?
Yes, sir.
Okay. What causes tropospheric ducting? We talked about that before. Temperature inversions in the atmosphere. You might think that as you go higher up, the air gets colder. Well, yes, except when it doesn't. Sometimes you'll start going up and then there'll be a temperature inversion. I would encourage you that after you get done with all this, you take weather spotting training from the National Weather Service. They'll talk about all these things and tell you a lot of things more about the atmosphere than you ever want to know, but they're really good about explaining that. Okay. What is generally the best time for long distance 10-meter band propagation via the F region? Okay, from dawn to shortly after sunset during periods of high sunspot activity. Now, why is that? Well, first of all, high sunspot activity means that the sun is putting out more energy in the form of electromagnetic radiation as well as particles, charged particles. When do this radiation and the charged particles hit the Earth's atmosphere? Basically during daylight hours. And that's what we're talking about here, from dawn to shortly after sunset, because there's a little bit of lag there. So you get that period is going to be the best for long distance 10-meter band propagation, which is why 10 meters is a lousy band to use during the solar minimum, when you have the fewest number of sunspots. Solar maximum, it's fantastic. You can actually do 10 meters almost around the world. But in solar minimum, which we just came out of, it's not that great. Which of the following bands may provide long distance communications via the ionosphere's F region during the peak of the solar spot cycle? We just got done talking about that, 6 and 10 meters. You got to realize 6 and 10 meters are almost like, well, actually 6 meters is a VHF frequency or band. 10 meters is real close to it. So they're almost line of sight unless you have a very high concentration of ions in the upper atmosphere. Why is the radio horizon for VHF and UHF signals more distant than the visual horizon? Again, this goes back to, remember how we talked about how radio waves can be reflected, but they also can refract? Well, that's what happens with VHF and UHF signals. They bend in the atmosphere. They bend around the Earth. Now you get about 8% difference between the visual horizon and the radio horizon. So it's not much, but you will get a little bit of refraction there. Okay, that's it. You have 3 questions from all those. There's like 30 some odd, 33 questions or so. Questions? I'm going to stop sharing here for a moment so I can see people. People can see me.
Frank, can you tell them which 3 questions though?
Of course I can. It'll be real simple. It'll be one of those 33 questions. The 3 of them, one for each section. You have a 1 in 11 chance of getting the right one.
I live in a village, and I mean, normally use VHF. Notice when the weather is down, the VHF signals go bad.
Well, yeah. VHF is probably the most used band that we do in amateur radio. You have basically fairly good, reliable equipment, and it has fairly good propagation for what you need. One way of looking at it is that the equipment doesn't take a lot of space, a lot of power, and you can get good transmission and reception with it. There's a reason why there's probably more activity on VHF than there is any other band. Okay, now I don't know which one of you are actually students and which ones are the Elmers and whatnot, but let's go through them. Emery, do you have any questions? You'll have to,
I do not have any questions, but thank you so much for the wonderful presentation.
this is like high school physics. I have a PhD in physics, so I love this stuff. So I mean, yeah.
It's definitely very intriguing.
Okay, how about, oh, I got a phone number here. I don't know who that is. Who's phoning in? Yep. Anita,
Yes.
any questions?
Nah, like Emery was saying, this is our review time.
Yeah. And by the way, if you are not doing your practice exams or the flashcards, you ought to be doing them because a lot of the stuff is really easy to pick up once you start doing the flashcards.
Okay, great tip. Thank you.
Yeah, I always encourage people to use the flashcards. Okay, let's see. Linda, I'm not going to ask you. Marlena or Marlene?
Marlena?
Marlena, okay.
No, I do not have any questions, but thank you very much and thank you for that wonderful tip. The flashcard, I will do that.
Yeah, I know some people do ham study. I've always encouraged people to use hamexam.org because it's free. And they all cover the same material. And they'll know what the questions are and what the answers are. So it shouldn't be that hard. Okay, who else is on the line here? Well, Steve, anything else?
So we have Galaxy S9 Plus. I don't know who that is. I suspect it might be Timothy.
No, that's Michael.
Michael.
Okay,
Mike,
Michael.
any questions?
So Michael, are you on twice there in the list twice, both as a phone number and Galaxy S9?
Yes, I logged in with the 628 number.
Okay, so all right. Yeah, I heard you on the phone number. I recognize the phone number, but I wasn't sure what the other one was coming up as.
Yeah, Timothy, I sent him the picture of the some part where to log in and ID. Hope he got on.
Okay, so he might be there, but I don't see any microphone indications, so maybe it's just listening only.
Yeah, he might be on. Hopefully he went on.
Okay,
Well, I don't know if everyone has my email address or not, but if not, Steve, you can get it from Steve. If you have a question, you're more than welcome to send me the question. I'll give you the best answer as I can.
So I'm going to go ahead and stop the recording and then pick it back up when we start with the presentation.
Yep, the WinLink one.
thanks, Ray.